Okay, we're going to be looking at section 8.2, which is going to be techniques of integration involving trig functions. And this is moving beyond integration by parts. Integration by parts, of course, is a very useful technique, but there are many integrals, particularly those involving trig functions, where we're going to have some other methods. And let's just remember that we did, in a previous chapter, actually break down the integral of tangent. We thought of it as sine over cosine and did a u substitution. It's such a reoccurring kind of a trig function that it's well worth memorizing, and we want to memorize that the integral of tangent could be thought of as just the natural log of the absolute value of secant of x plus a constant, or you could even have a negative out in front, the negative of the natural log of the absolute value of cosine of x plus c. So memorize this. It's going to show up enough that it's well worthwhile knowing. The same thing with secant. We're going to memorize this as well, but let's actually prove what the antiderivative of secant is. And what we're going to do real quickly is multiply through by a helpful form. I do want to say this much, that even if you would have done integration by parts, it really wouldn't have been helpful. You could have tried different use substitutions and so forth. But what I'm doing right here is I'm multiplying actually by 1. Secant of x plus tangent of x over itself. And if we were to distribute up on top, we'd get secant squared of x plus secant x tangent x. And then we'd have our denominator just being the secant of x plus the tangent of x. Now, at first glance, this might seem like we've just made this whole process a lot more complicated and way messier. But let's try a u substitution. Let's let u be our denominator of secant of x plus tangent of x. And if we took a derivative, du would be secant of x times tangent of x plus, well, the derivative of tangent is secant squared of x. And if you're really on your toes, you're going to see that this right here, the secant x tangent x plus secant squared dx, is really what we have in our numerator of the integrand. And that means that we will have 1 over, well, secant of x plus tangent of x we called u. This whole numerator is really just going to be du. This would become the natural log of the absolute value of u plus c, which, resubstituting back in, is the natural log of secant of x plus tangent of x in absolute value plus a constant. Wow, that is what you want to have memorized for the secant of x dx, for that antiderivative, for that integral. They'll show up enough that it's well worth knowing. That being said, I hope you remember from previous classes, both in accelerated geotrig and accelerated math analysis, that there were some basic trig identities that we really need to be familiar with. The first 3 up here are known as the Pythagorean identities. They're coming from sine squared plus cosine squared equals 1. But sine squared, another name for that would be 1 minus cosine squared. Cosine squared, similarly, is 1 minus sine squared. And then, of course, the very famous, we'll use this a lot, tangent squared plus 1 equals secant squared. The bottom 2 are known as power reduction identities. We've also seen them in an altered form as half angles, where we could let 2x be represented as a, and then x would be a over 2. And you'd have 2 half-angle identities for sine squared and for cosine squared. We want to remember these. They're going to prove to be very helpful. But commit these to memory as well. There's a lot of memorization in these integrals that we're working on in this section. Here's something that I'd like to suggest. Whenever you have an odd power for sine or cosine, we're going to talk about this more in a moment. Odd powers of sine or cosine, here's a wonderful suggestion. Take an odd factor out, take out a cosine of x or whatever it may be out to the side. And once you see that, it might look like you've made the problem a little bit more complicated by doing that, but you're about to turn it into something much, much nicer. Cosine to the fourth of x is really cosine squared of x, whole thing squared. And then once you have this squared property, cosine squared of x, come right back up here to our Pythagorean identity, and we can see very quickly, well, my goodness, right now we can look at that as 1 minus sine squared of x, whole thing squared here, times the cosine of x, dx. Now, again, this looks considerably more complicated than what we just started off with, perhaps, but now we can do a wonderful u substitution. If you're really on your toes, I think you can see where we're going with this. Let's let u equal the sine of x. If that's done, then we can say du is equal to cosine of x dx. And immediately you will get a new integral, 1 minus u squared, quantity squared, but cosine of x dx, this whole thing here, really can just be written in terms of du. So you can see how taking away one term of this odd power and then using the Pythagorean identities will lead to a helpful u substitution. Let's expand real quickly. As we expand 1 minus u squared squared, this would become 1 minus 2 u squared plus u to the fourth du. And if we did a quick antiderivative term by term, we'd have u minus 2/3 u to the third plus u to the fifth over 5 plus a constant. One last step. Let's resubstitute back in. U is just representing the sine of x. So very quickly we can come up with our final answer being sine of x minus 2/3 sine cubed of x plus sine to the fifth of x over 5 plus a constant. And it works out pretty nicely. When you have an even power, however, even powers, when you're starting off, you want to go to the power reduction theorems, the power reduction identities. And that means immediately we can take note that sine squared of x can be thought of differently as 1 minus the cosine of 2x all over 2. So immediately a power reduction is going to lead us to a simpler integral. Let's deconstruct this fraction. In class we call this I heart math so very often. It's cosine of 2x all over 2. And now, quite simply, we can immediately take some antiderivatives. This would be 1/2 x. Now the antiderivative of cosine of 2x, you might expect for there to be a sine of 2x in there, but we're going to reverse the chain rule. The chain rule, if we took a derivative, would involve multiplying by a 2, the derivative of the inside. We're actually going to divide by 2 since we're taking an antiderivative. So dividing by 2 is the same thing as multiplying by a 1/2. Double check that this is correct by quickly taking a derivative. You can see that the derivative of 1/2 x is 1/2. The derivative of the sine of 2x is cosine of 2x. Out comes a 2 from the chain rule. The 2 would cancel with the 1/4 to make a 1/2. And sure enough, we're good to go. You might wonder, of course, what to do if our even power might be a little bit higher, perhaps like a fourth power. And not surprisingly, we are going to use the other power reduction formula up here, cosine squared. We're going to have to get to that in just a moment, though. Let's see how we might proceed. What you'd want to do, of course, is to think of this as cosine squared of x, quantity squared. And if we did that, of course, we'd know that this would become 1 plus the cosine of 2x all over 2. And, of course, what we can do very, very quickly then is to square this integrand. Squaring the top, you'd get 1 plus 2 cosine of 2x plus cosine squared of 2x. Our denominator, of course, would just be a 4. And right now, this is looking promising. Let's continue up here. And we can deconstruct this fraction. We can do that I heart math, so to speak. 2 over 4 would just be a 1/2. So this is all looking very promising until perhaps we get to this last term where we'd think, well, my goodness, now we've got a cosine squared still. Well, here's where, once again, we can use our power reduction formula, but we have to be very, very cautious as we're moving here. Please understand that another way to write this power reduction formula, if you look back up here, what I've just circled, let me just say that I wrote cosine squared of w would equal 1 plus cosine of 2w all over 2. And you might wonder why I changed the variable from an x to a w. I'm letting the w be in there to represent whatever the argument would be. The reason why I'm doing that, of course, is I want to point out that right now, inside of my cosine squared, I no longer have simply an x. Right now I have a 2x. And that changes everything, really. So let's see if we could quickly make an adjustment. I'll have my 1/4 out in front here. Then we'd say 1 plus the cosine. Well, we're going to have to double whatever was inside. If I double a 2x, I'll be out to a 4x. And then down below we'll have our 2. Well, at least right now, every power of cosine is down to just a first power. Our arguments are different, of course. Deconstructing, doing an I heart math, deconstructing our fractions, we'd have a 1/2, which multiplies to 1/4 to get you 1/8. And then we'd also have a 1/8 cosine of 4x. Almost done. Look, a 1/4 and a 1/8 right here, if we add those together, 1/4 is really 2/8, and 2/8 plus 1/8 is 3/8. So we're close to finishing up now. We're just going to have to take some antiderivatives and reverse the chain rule. So finishing this problem up, it should only take a moment to do that. The antiderivative of 3/8 would, with respect to x, of course, would be 3/8 x. Reversing the chain rule here, if I took an antiderivative of cosine of 2x, I'd have the sine of 2x, but I'm going to have to divide by a 2 here, and 1/2 divided by 2 is 1/4. Antiderivative of cosine of 4x is sine of 4x, but instead of multiplying by 4, I'll divide by 4, and I'd get 1 over 32. 1/8 times 1/4 is 1 over 32. Add a constant, and hey, look at that. This would be our final answer. So if we flip over to our next page, we're more or less summarizing some guidelines that we just saw. Let's say that m is an odd integer and we have sine raised to an odd power, where we have sine and cosine inside the integrand. Take one term of sine away, take that one factor out, and then you'd have sine to the m minus 1, where it's an even power now. Then we go back to our Pythagorean identity with the even power, and then we're able to make a u sub